All right, so I'm going to go through this next presentation in two parts, and these are, for the most part, the core of our training slides that we do in our ongoing training for PowerWorld Simulator. The first few slides are very similar to what Tom had talked about. I'll talk a little bit about kind of how we got to where we are as far as with what's going on at NERC. And in 2012, they released this report right here, which had some recommendations as far as what the industry should be doing in order to study these events. And it called for improved tools for industry planners and system operators to study GMD and prepare for the impacts. And then also just some framework for exchanging information between researchers, and also looking at the need for a new reliability standard. FERC got involved. In 2013, they issued this reliability standard, and they also directed NERC to put some procedures in place. And of course, they usually end up impacting the operations side kind of first, and then the planning side comes in with requirements for study. The NERC TPL 007-1 came out of that, and it mandated the need to study a benchmark GMD event, which we'll talk about a little bit later, and putting plans in place to look at those impacts. So, and there's basically two concerns. One is that you can have, because of the VAR losses in the transformers, you can have some instability, some voltage depression, and possibly cascading failure. And then the other concern is the transformer, the heating that develops in the transformers, and whether or not that causes either an immediate failure, or if not an immediate failure, perhaps some damage that accelerates the loss of life in the transformer. So NERC, some things about NERC TPL 007-1. There are several requirements. Some of the key ones that impact us are the need to maintain models. So we've already got the AC system model with our power flow cases. I need to add some GIC specific data in there, and then the need to complete the vulnerability assessments based on the benchmark event, and so forth. And there's a task force. A lot of work was done in 2012 and 2013 on this task force, and then it kind of went quiet for a while as the industry and FERC debated what to do with it, and it's starting to wake up again. There's some new activity because of what happened here. So FERC followed up and then made a follow-up order that basically just directed a few modifications to the TPL 007-1. One of them being that the benchmark event shall not be based solely on spatially averaged data. So in other words, the idea that as Tom was mentioning, that you got 5 volts per kilometer all over the West is perhaps not the best assumption. You should also study situations where you have areas of high GIC, and maybe the rest of the system is not so much. And we're starting to put that sort of stuff into the software as well, where we call it a hotspot that you can model. So you have a general condition that's continent wide, and then you can model a hotspot. And I guess the questions are, what are the parameters for studying that hotspot? Do you have to move it around, every few degrees of latitude and longitude, and study different possibilities there? And that's one of the things that the NERC GMD task force is going to undertake going forward, is looking at these issues right here. Okay, so this was, Tom discussed this information here. So, and Tom touched on some of this stuff as well, as far as additional data that needs to come in. So the line resistance, we have that in the AC power flow model. The software also allows you to put in a separate DC resistance if you want to specify a DC resistance from the line. But generally, if you don't have that information, or you don't have the resources to put it in there, you can just you can use the value that's derived from the AC resistance that's already in there.
Question for Scott.
Yes.
Just to be clear, all of these can be inputted into base package a simulator, right?
That's correct. The data capability is there, right? We have a GIC add-on, which is the analysis side, but the data fields are there if you just want to store them in the case. And then we can also export to the PSSE GIC format, which is just a text file with a GIC extension, and read data in from that format as well.
Okay.
So other parameters that are needed, the substation geocoordinates, so the latitude and longitude of the substation comes into play because that is a key input in determining the size of the battery that we stick on the transmission line to model the GIC. The grounding resistance, as Tom mentioned, also transformer configuration, coil resistance. The core type is important for determining the K factor, and of course you could just put in your own transformer specific K factor as well. Whether or not it's an autotransformer, as we'll see, that governs the topology of the transformer. And information on GSUs, of course, is important. And sometimes, I guess that's kind of a separate piece because sometimes, or very often, the generators have separate owners, and you may not have access to that within a given utility. You may have to reach out to generator owners in order to get that information. So, and the way it's handled in simulator is generally buses are assigned to substations, and substations have the coordinates. So, yeah, as far as how do the K factors work and how do we map the transformer GIC to reactive power losses, as Tom mentioned, it's really a transformer specific thing. There are some default assumptions that you can put in, and then you can classify your transformers by type, and then for each type of transformer you can say use this K value. These defaults are all in simulator, and you can change them if you want to. If you want to change like the global K factor that it's applied to a 5-leg transformer, there's just one spot in simulator. You can go and just change that, and it'll apply that K factor to every transformer of that type. And then you can go down to the individual transformer and give it its own value too. If you don't know what type of transformer it is, it'll be assigned a type of unknown, and then generally it'll get the kind of the worst case K factor, which is the single phase. But again, you can
depends on the voltage. If it's high voltage.
Right. It's a per unitized K factor as well. So. Okay, so the starting point is modeling a storm scenario, and we'll get into that in the example as we go forward too. And the outputs that come, so when we solve for the DC network, and we get the we saw that G matrix and the matrix equation that Tom showed earlier. The first thing that comes out of it is the DC voltages for the substation neutrals and for the buses in the system. And then from that, it can calculate the currents that are flowing through the system. And then the currents get mapped, the currents in the transformers get mapped to megavar losses by way of the K factors. And that's how you do the AC analysis from that as well. So Tom mentioned this 4-bus example, and we'll go ahead. I'll just open this in PowerWorld Simulator, and if you want to follow along, you can. Otherwise, you can just watch it up here as well. So I'm going to do these examples in PowerWorld Simulator 19, which is widely available with right now. In Simulator 20, Tom's going to talk a little bit later about doing the EMP modeling, and we're adding features that are only available right now in Simulator 20 for that, but that will be released sometime in 2017, so that'll be out there and available soon as well. But the case I'm opening is the B4 GIC case. And we'll go to our add-ons ribbon and then open the GIC dialog right here. It's just got an icon with the sun on it. And the first, you can kind of work your way down through the screens right here. This first one is where you put in information about the storm scenario, and we'll get into these. The calculation mode, the single snapshot calculation mode, just pretty much allows you to put in a uniform field. And then you can also scale the uniform field, which I'll talk about a little bit later, by geomagnetic latitude and then also by the 1D Earth models. And you have to import those. In this example, we won't quite touch on that yet. We'll just use a uniform. You can also put in time-varying fields with this second mode right here. And we'll talk more about that later when Tom talks about doing EMP modeling, because the time-varying nature of that becomes pretty critical, because in an EMP event, it's much shorter-lived, typically, than a solar-induced GMD, but the rise times are a lot quicker. So the currents still look like DC relative to 60 hertz, but you get rapid changes in the field, which are best simulated in a transient stability time frame. So more on that later. So the input data for substations, the tables and results have both input and results data after the gig is calculated. If I go into the substation tab right here, I'll see, make this a little bit bigger. There's two substations in the case. There's just one on each side of the line, and there's two buses in each substation and a transformer in each substation. So those are represented here. We have the latitude and longitude of the substation, and then we also have the grounding resistance right here. And if you put in a 0 value for the grounding resistance, then simulator, that's the default. If you open a brand new power flow, WEC power flow case, and there's no information in there already, these are all going to be populated with zeros, and then simulator will come up with a value. You actually have to, I think, recalculate. The default is going to be between, I think it's 0.1 ohms and 2 ohms, and it's going to be based on the size, the number of buses, and the highest nominal kV, which is not really a good guesstimator for grounding resistance. But we put something in there just for the benefit, so that if you don't have information, you can take a case and just start doing analysis. But really, that information should be refined either with measured values, or you could do your own parameter sensitivity analysis where, for example, you study it once where you assume all of your substations have a certain value, and then you change that value, maybe double it, and see how that affects everything. But in this simple example, just so the numbers are nice and round and so forth, we use the 0.2 ohms to put in there. So then when we click the Calculate GIC Values button right here, did I not put a storm in yet? Let's see. Okay. Yeah, we got to put 1 volt per kilometer in. There we go. Okay, so yeah, just make sure that information's entered. And then you can also click, go ahead back up to this page right here and click Calculate Maximum Direction Values, and then also include the GIC in the power flow. And what the maximum direction value will do is it will tell you for different devices what's the worst case storm scenario. So for example, for a transformer, what's the worst case? We can look at the transformer inputs and results down here on the transformer tab. And there's 2 transformers in the system. They're both the coil resistances are shown here, and then the configurations, grounded Y on the high side and delta on the low side. When you open a new case, they'll all be set to unknown, and then simulator will go through. There's a couple slides that I have later that I'll show you, kind of a decision tree grid that simulator will use to guess on the configuration if you haven't populated those, but then you can populate them as well. Whether or not the transformer is an autotransformer, and then the core type, and then the K factors are over here. So moving back over here to the left in this dialog, this has some of the results as far as the per phase effective amps, and that was the quantity that Tom showed you that's dependent on both the high side and the low side currents, as well as the turns ratios, and then the megavar losses. And then it also tells you like what the maximum megavar losses are for each transformer. What's the worst case megavar losses that you could have, and what orientation corresponds to it. Now in this case, because there's just one transmission line and there's two substations that are on an east-west orientation, the 90-degree storm direction is in fact the worst case, which is what we entered. Actually, what I should have had you do is enter a storm direction of, say, 45 degrees. And then if you do that, it'll still tell you, so 45 degrees is going to be, the dot product will be, what is that, the square root of 2 factor for the cosine there. So the GICs are going to be lower with a 45-degree orientation, but then it'll also tell you in the results, if I go back to that on the transformers, it still clarifies that the maximum direction is 90 degrees, which is, makes sense because that's the orientation of the line. And then if you look at, there's another tab here called System Summary.
Can you go back to the transformer?
Sure.
That K value again?
Okay. Yeah, I'm sorry. I'm kind of whipping through that to keep up with time, keep up on time. But there's some slides on that as well. But yeah, the K factor's over here. So question about it. It's a piecewise. Let me come back to that because there's a picture that shows this a little bit better. But yeah, the K factor information is over here.
And you said the max was at 90 degrees, but it would also be the same at 270, correct?
Right.
180 degrees.
0 to 100. Yeah. Yeah. It's going to give you a value between 0 and 180 or 179.9, because if you flip it, if you change the direction, the impacts on megavar losses and everything else are exactly the same because the transformer doesn't care if the GICs are coming in the ground or out of the ground. So
when the program calculates the max, does it rotate through 360 degrees or 180?
Probably 180. Yeah.
180. Yeah, because it is symmetric with respect to 180 degrees.
Yeah, and you can put, if you want to, you can put an orientation of 270 degrees in, and you'll get the current going in the opposite direction, but then the quantities for megavar losses and the effective GIC and everything else are exactly the same. So the effective, there's quantities for transformers, like with high side coil current, and that'll be a signed value, which will depend on whether it's coming into or going out of the transformer. But then the effective GIC quantities are always unsigned. They're always just, absolute value. And of course, the megavar losses are always positive as well. And so, yeah, back to the slides. So those are some inputs for substations. Just a little bit about, again, on the assumptions that we make if you don't put a grounding resistance in, that's kind of described right here. The best way to do it is to use measured values. Because as Tom mentioned earlier, though, the real world is more complicated than just making one simple assumption. And you may have situations where the grounding resistance might vary depending on the moisture, time of year, if there's more water. Yes?
I was wondering if you've done any parameter sensitivity. Which ones are the ones that are like the most sensitive to the GIC currents? Like, is it the grounding resistance? Is it actually putting in the DC resistance of lines? What all of the different parameters that go into the simulator for these studies, which are the ones to really focus on because they make the largest difference to try to get right?
We actually did sensitivity analysis. We did an IEEE paper on that, and it varies. When we started doing this, we thought, the grounding resistances, they couldn't matter that much
turns out they matter a lot. But it depends. It really depends on the location.
The thing, yeah.
If we have measured values of those, that would be what
Better.
we really focus on getting in there, right?
Yes.
Bigger deal.
Yes.
Yeah, we can tell you which substations. The larger substations are more important than the little ones. You know, a 500 kV substation is going to be more important than a 115 kV substation.
If you got more transformers and more lines coming into it, it's probably going to be more significant than. And really, if you have, for substations that have no grounded transformers, you don't need to put, well, this is coordinates right here. For grounding resistance, where's that? Yeah, for transformers that don't have any transformers or switch shunts that you're modeling, no connections to ground, you don't need to put the data in for those, of course, because it's not going to be part of the G matrix anywhere. So, yeah, the coordinates, this, of course, is something that's not going to be in your FERC 715 model, but hopefully the industry is moving to where you're starting to keep that information. And I think it is supported now in PSSE and in the EPC format. So
it's been painful to reach this.
Right. Yeah.
Like it's really a secret. You can go on Google and find it.
That's pretty much how we do it when we're building a database, exactly. So the need to put in a substation coordinates applies regardless of whether or not the substation has grounded transformers. So you can't, if it has at least one bus in it where you're modeling a GIC equivalent DC voltage, and I kind of skipped over that up to this point. There's this tab right here in simulator under options where it says DC current calculation. There's a parameter right here where you put in the minimum voltage level to include in the analysis. And what that means is any transformer that operates at that nominal kV or higher will put in one of those DC battery models on that line. So the default in simulator now I think is 50. NERC has been using a 200 kV. I think it really should be lower than 200 though, because I mean it doesn't matter how it doesn't the GIC doesn't care what the AC voltage of that line is. If it's a long line or even if it's a short line or a medium line, it's potentially going to induce a GIC voltage on it. So NERC has been working with 200 kV and above, so you could put in 200. But basically, any substation that you have where you've got a transmission line coming into it that's at that level or higher, you should have coordinates for.
Scott,
Yes.
if I might just for a moment speak to that, completely agree with your viewpoint, and I would point out to folks that Avista, PowerWorld did a study on this for us, what was it, 4 or 5 years ago. Then subsequently we licensed the software, did a study, helped EPA do their study. And I can tell you what our system does, our 115 and 230 system, nicely sources GIC to Bonneville's 500. And if you were to exclude our 115 system, we tried it.
You get much different answer. Yeah.
It's wrong.
Right.
Right. So this idea that 200 kV and above, why bother? Just say it's unavailable. There is no GIC. So, I mean that's something we have to feed back based on testing the field, so to speak, from doing the analysis. It's a terrible idea.
I think it originated from when people started looking at this issue, and before we started putting these tools into the software, and now, we did it first, Tom did it first, and then, PSSE and GE, PSLF have the tools now, everybody has the tools. Prior to that, I think what they did was they just did kind of back of the envelope spreadsheet calculations where they said, here's our major substations. Here's Bridger and here's Cooley, and then just connect the dots and say, okay, we got a 500 kV line here, and they just did hand calculations or spreadsheet calculations. And so if that's the case, then yeah, you're really simplifying your life if you just look at 500 kV and above, because you might have tens of substations. If you start looking at the lower levels, now you got hundreds or thousands of substations, and it's
and some of it was based on what Louis Marti did at Hydro Ontario Hydro. So it might have worked for their system, but not your system.
Yeah, I mean, it's just,
And that he had a lot of influence in that document, and
Right.
he speaks from his system.
I mean, in this part of the world, the 115 was first, and then 230 was overlaid on top of that to raise up modules, weird stuff. 345, pack nodes, and then 500. And it's just, to strip out that, wow, why bother?
Mhm.
We're not going to have accurate answers at all. So,
Well, and as I recall from looking at the Bonneville system back when we did the 115 kV network along the coast, if you go between west of Cascades in the coastal areas,
Right.
actually becomes significant when you look at that. So
The standard right now is written just 200 kV and above for the
Right.
data to supply.
I think that's the NERC standard right now. Yes.
Yeah, then
So-
he said, well, why bother? It's silly standard. If that's all that's ever supplied, and then you.
yeah, I mean, if you're just
Yeah.
compliance centric, you can turn the crank and move on. The objective would be something value.
Right, yeah, then you want to put all the data in.
So from your experience, on the lower kV 115, 161 kV systems, the lines are much shorter compared to the large, longer transmission lines. The transformers scattered everywhere. There's a lot of impedance on the system. For the same 5 volts or 10 volts per mile kind of default number, including all that information, will actually change the results.
Well, certainly having a shorter line is going to attenuate, but it's still a network, and if it's still a source for GIC. I think it's also significant from the standpoint that at a lot of those levels you don't have VAR resources from generators to help offset megavar. And I guess the way it works, we're still, even if you're not modeling a DC input voltage on the lower voltages, it's still a network, and simulator will still model the flow of GIC down into that network that originates from voltages on other lines. So it's not like the network's totally going away, but it could be a significant effect in some parts of the system. I think, mainly because of the fact that it often correlates with lower VAR resources. If you've got big GIC at Grand Coulee, that might be a big deal for the transformers that are affected thermally. But from a system standpoint, it might not be so bad because you've also got a lot of VAR resources spinning right there to help prop the voltage up. So.
Does the age would matter? Age of the transformers, how old they are? Would it be affecting the result of?
I'm-
I think it has
Not
more of
sure
an
that affects
effect on the temperature and things like that than the aging than it does on the GIC.
Thermal aging is
Yeah.
where you're in trouble there.
Consideration for like underground transmission? Like how that affects it?
It doesn't have much difference whether it's underground or above ground because the electric field is the same up on the towers and underground.
Okay, so with transformers, these are the key inputs right here, and you put all that information in on the transformer page. You can see that we have from that dialog, we have the high side and the medium. So we call all transformers, they're identified in the dialog as having a high, a medium, and a low side. For most transformers, the low side is going to be delta connected. Usually, if there is a tertiary in the model, we're going to assume that it's delta connected. So it's not as important to put in the parameters for that. But certainly anything that is got grounded Y, you'll want to have the ohms per phase populated if possible. If you don't populate it, then there's a slide here that shows how it derives it from the AC. But of these inputs right here, the two that are really key is what the grounding configuration is and whether or not it's an autotransformer, because this really determines the topology of the network.
Question on that, Scott?
Yes.
That would be a tertiary that would run out and plug into something, not a stabilizing line. Right? We don't need to do anything with that.
Right. Well, really any tertiaries, we're generally going to assume that they're delta connected. But yeah, there's some that I guess that are not that might exist in the field, but don't exist in the model.
Like a tertiary we use for
Right.
call them stabilizing lines, but we don't bring them out.
Right.
So then we just ignore that.
You can ignore that, yeah. But I was just explaining why we call it a medium side, because there's three fields. There's a high, medium, and a tertiary. So that's, I mean, you might think of it as a high side and a low side. The low side is probably the medium side on the dialogue, is all I was pointing out. Okay, so yeah, you can, for the coil resistance here, you can tell it, there's a field for saying, do you want to manually enter the coil resistance or not? If you say no, then this gets grayed out, and the value that it uses is derived from the AC resistance. Whether or not it's an autotransformer is yes, no, or unknown, and then the core type. So for the coil resistance, it's going to use this equation, two equations, to estimate how the AC per unit resistance for the transformer. It'll split that between the high side and the medium side if you don't put in a coil resistance for each winding. If you do put a value in for each winding, then this equation is not used. It'll use the value that you put in. Just a picture describing an autotransformer and why it's important to, if it's a generator step-up transformer or it's a load-serving transformer that's delta on the high side, then it's really simple. If it's delta on the high side and it's a load-serving transformer, then that's probably going to block the GIC from most of the network because you have that open circuit on the delta side. If it's a GSU, you really have just one coil, the high side coil that comes into play. It's probably grounded. If it's an autotransformer, you have a situation where you have a series winding and a common winding, and the high side is up here and the medium side is down here, and then you can have GIC that flows all the way down through here to the neutral. It's really like a three-terminal device for the GIC. You can have some coming in this way. It also means that if you block the neutral with capacitive or resistive blocking down here in the neutral, that you're not going to get rid of all the GIC because it can still flow through here. So the high side, the parameters that you put in into simulator for the high side is just this piece of it right here, the resistance of this part of the coil, and then the medium side is the resistance for this part of the coil. So there's also on that DC current calculation tab that I showed earlier where you can specify the minimum voltage to include for putting the equivalent DC on. There's also some parameters that you can put in for estimating whether or not a transformer is an autotransformer if you don't specify it. Again, if you specify it on a transformer by transformer basis that this is or is not an autotransformer, then none of this is used. It'll use the data that you put in. But if you leave it as an unknown whether or not it's an autotransformer, then it'll look to these parameters, and you can adjust those parameters as well. The defaults are 4 for the turns and 50 for the voltage, and then that's explained here. I'm going to kind of try to move through this here. Get to our break. So the configuration, there's also, for load serving transformers, you can put in a default configuration for the high side and the distribution side. The simulator defaults are the high side is delta, but you can change that if you want. You can also change these on an area-to-area basis as well. So there's some explanation as to whether or not, how simulator guesses whether or not you have a GSU or an autotransformer or something else serving a load. Tom talked about this per unit stuff earlier. So the K factor, you can enter it. If it's left at default, then it's going to be based on the transformer core type, and it'll look up the values that it looks up from the transformer core type are on this tab right here called AC power flow model. So these are all per unitized, and there's 3 parameters. There's a first segment, a breakpoint, and a second segment. So you can put those in, and graphically it looks like this. So you put in the slope for the K factor. The horizontal axis is the effective GIC current in per unit. The vertical axis is Q loss in per unit, and then that gets converted into megavars based on the S base, the power base. So these are the values that you're putting in, and then this is the third parameter is the breakpoint right there. So those are the defaults. And current calculation, kind of skip through that. And then for transmission lines, you can, there's a tab in there for inputs and results on transmission lines. You can tell it this manually enter line resistance if you want to put in your own ohms per phase DC resistance. You can change this to yes and then put your value in here. Otherwise, it's just going to convert it from the AC value, and it's going to assume no skin effect from between 60 hertz and DC. So if you want to adjust that and put in a skin effect, then you would have to put in your own resistance, DC resistance. Okay, on the areas tab, I'm just going to kind of move through the slides here and probably not go back to simulator for the rest of this example here. But on the area, this is also under tables and results. For individual areas, you can tell it whether or not to include the GIC losses and whether or not to include DC volts. So the DC volt, that's the induced voltage on the transmission line. If you wanted to study everything in the whole Western interconnect, you would just leave those set to yes for all areas. A lot of times what we'll do, if we're studying a particular part of the system, is we'll put DC input voltages everywhere in the system, but we might study megavar losses on transformers just in certain areas. The rationale behind that, meaning if you want to use the study as a way to determine where the weak points are in your system. If you include VAR losses everywhere, and you've got a uniform field everywhere, you could end up with voltage collapse that is caused from some other part of the system. And so if you want to study where the weaknesses are in your system, then you might want to ignore GIC losses outside of your system. So, and then on areas, you can have these different, these are the same as the global options for the default transmission distribution system. You can have area-specific values for that, and whether the transmission side is delta connected or GY connected for load-serving transformers, that can be different than the global assumption. The G matrix, this is the conductance matrix, just real terms, as Tom mentioned earlier, and it looks a lot like the power flow Y bus, except it's just real terms, and then also it's augmented with substation neutral nodes, as well as all the buses in the system. So if you want to look at that, that's here, G matrix. And so the diagonal terms are just the sum of the three-phase conductance of all the incident devices, and the off-diagonal terms is the conductance between those nodes, the negative of the conductance between those nodes. So then Tom talked earlier about how that's solved. And then we'll get into an example later where we look at the benchmark event, but there's these, in the NERC, it's described as an alpha and a beta factor. Alpha is for geomagnetic latitude, and beta is the 1D Earth model. So you can optionally choose to include those factors as well. So we'll do another example with that later. And then if you choose to include the GIC in the power flow, that's this checkbox right here. After you solve for the GIC values, you can solve the AC power flow. Up here, I can just click my single solution button, and then you can see how AC bus voltages are impacted by the megavar losses. And then also how other devices respond to, like generator VAR outputs and things like that. So if I clear this box and solve it, then I'll get different values. Yeah, question.
I was just it seems probably the difference case would be pretty useful for that. You can just do a before and after comparison.
Exactly.
I would
Exactly.
ask if that was like a built-in thing, but it's probably simple enough to do just on your own.
Yes, it is, and I'll get to the second example, or one of the later examples I'll get to later. We'll do that. So we talked about the maximum direction values. Okay, we also recently added the ability to put in some resistance for switch shunts. I'm going to skip over the details on this in the interest of time, but it's described here on the slides. It really only applies if it's a inductive shunt. If it's capacitive, simulator is going to assume that it has infinite resistance or zero conductance. There's also no K factors that we model for the switched inductors because we're assuming they have air cores and they don't saturate, but they do still, they can provide a path to ground through the substation neutral. So you could put in a resistance for that. Pardon?
The only air core ones I know of are a Vista system, and the rest of them are oil filled.
Okay, so it's
It's not magnetic.
I don't know if the math.
Yeah, non-magnetic.
the oil filled is for capacitive devices, though, or for
No, the reactors.
okay.
Like giant single bank transformers full of oil. Bottle's got a bunch of them catching on fire lately.
I guess you could model those as a I mean, what we told customers to do before we put the ability in there to enter a resistance for inductors is just to model it as a transformer against a dummy bus.
But it's not.
So I guess you could still do that.
It's just oil and it doesn't have a magnetic core. If it's
Yeah.
saturated.
There's no magnetic core, though,
That's
right?
true.
Yeah.
So just big winding.
Non-magnetic.
All right, so that's
Yeah.
appropriate then.
So in this 4-bus example, if you put this into the system, you can see how the G matrix is altered. These 4 values are altered between the substation and bus 1. So
Is this matrix calculated or entered?
no, it's calculated. It's just there for you to look at if you need to. Okay. So yeah, there's also options to do some time varying inputs, and this is a good place to break. So, any other questions on that piece?
Is there a NERC standard event somehow defined?
Yes.
Seems like there should be one, right?
Yes.
Yeah, there is.
Yes. Yeah, we'll talk about that a little bit later. I mean, it's based on the Quebec 1989 storm, and it's scaled approximately by a factor of 4, because that was what was determined by space weather researchers to be a 100-year event. Of course, that's open for debate. They don't all agree on whether or not that's
You don't have
a 100.
Yeah.
Yeah, there's just not enough data points to say what's a 100 year. So it involves extrapolation based on what we do know and what we think the curve might be. So yes,
Is there an option to, or is this how it's done? The Q loss factors that are calculated, and there's the maximum Q loss depending upon the direction of the storm. Does when you're doing the combined AC solution, does it use the maximum or just what you had specified?
no, it's the current. If you wanted to change, it tells you the maximum so that if you wanted to change the orientation to the maximum for studying the whole system, at that point you could do that if you want. But for each transformer, the maximum is just for that transformer. So you change. Each transformer could have a different value. In this 4-bus case, they all have the same value because they're all connected to the same single transmission line. But if you have a network, then it can be different. And we'll look at a network example later too.
Yeah, I was just thinking if there's on a large system where there's hundreds of transformers, then some of them might be 35 degrees, some of them might be 75 degrees. It'll be varied.
Exactly.
There is no one thing to choose, but you could be, I guess, overly conservative and just grab the maximum for them all, and throw it into one.
Well, if you wanted to screen transformers out to for thermal analysis, you might look at the worst case GICs for each transformer and just say, on an event of a certain magnitude, if the direction is worst case, then this transformer could be impacted.
So you put in a storm direction at 90 degrees or 1, then you calculate from 0 to 180 degrees of the storm direction. Is that how it works, and report the maximum?
Yeah, because it's just it uses just the two. It's calculating based on a northward field and a eastward field. So and it can be superimposed. So
You can actually figure out the worst case then. It's all linear.
Yeah.
I can tell you the worst direction.
So it doesn't matter what you put in the storm direction, right?
Well, it uses the storm direction to calculate the actual values, but then because it's so simple, we also tell you the worst case direction.
Right. So the GIC values that you look at in any scenario are going to be based on the orientation that you put in. But then it'll tell you for each device and then also system-wide what's the worst case.
So it tells you the worst case direction for that particular.
Right, and for system megavar losses as well.
Okay. So
And for, I think, for area
so you can go
megavar
back to
losses.
that maximum and
Yeah, you could study that direction.
You can study the maximum if you wanted to then, yeah. I'll pick up here with some more information on what NERC is calling the benchmark GMD event. And this is a wave shape. There's a full time series actually that you can download from our website, and it's in an auxiliary file format. And we probably need to update it too because it uses the single snapshot mode that you just load in each snapshot with an auxiliary file, and then it can produce a time series for the transformers. It's not directly compatible with the transient stability tool, so we probably need to put in a new version of it that will work with our transient stability tool. But it will work with the power flow, and it can still give you a time series for transformers if you want to put those into a thermal model. So it's based, the benchmark GMD event is based on the Quebec, the event that brought down the Quebec power grid in March of 1989. There's a 10-second sampling, so it's, I guess, a little bit long for transient stability time frame, but it basically just linearizes within, between samples, it'll just interpolate linearly. And then this event was scaled based on some space weather researchers to approximate a 1 in 100 year event. And it's essentially by a factor of 4 of what the actual event was, because the peak in the actual event was around 2 volts per kilometer. In the benchmark event, it's scaled up to where it peaks at 8 volts per kilometer. And it's not uniform everywhere. It's 8 volts per kilometer at a reference location, which is in Quebec at 60 degrees north geomagnetic latitude, and also with the Earth conductivity in the Quebec region also, which is a highly resistive region. So to scale the field for any location in the US or Canada, you apply the 8 volt per kilometer peak times 2 factors, an alpha and a beta. The alpha is the scaling factor for geomagnetic latitude, and it can be computed from this equation right here. NERC also, in their application guide, I believe it is, has a lookup table in 5 or 10 degree increments, where you can they give you a constant that you can use also. So either way is okay. And then the beta is the scaling factor based on Earth resistivity, which for the moment we're using the 1D Earth model. Yes?
Scott, I was wondering, since a lot of this is based off of the 89 Quebec event, if a benchmark's been run where we take the Quebec system as it was in 1989, put in the 2 volts per kilometer GMD event, and see if we get the same things to trip or go wrong.
Yeah, as far as like the relay tripping, it's not something you can model directly in the power flow, I suppose. I mean, that's a lot of that's due to harmonic effects and things like that, which aren't modeled. So if you wanted to recreate the event with tripping, you would probably have to enter those events, maybe in the transient stability tool or something like that. It's not going to automatically come up with that. Certainly not in the power flow side. It's not.
Well,
but it's
see the same things that they saw as far as the whatever they had measured.
That was part of the problem. They didn't really have a lot of measurement. It's about a foot.
Yeah, I don't really know that that's an effort that NERC is pushing to try to like recreate the event. I think it's more of we want to estimate what a 1 in 100 year event could be, and then study it on today's system.
Right. It would just be a good validation of the tools and the process to say, oh yeah, if we had this at the time, we would have got exactly what happened. So this is worth pursuing versus, just kind of not having anything to go on.
Would be a good idea. Let's go on 5 minutes.
Okay, so we can do an example of this on a synthetic case similar to the one that Tom showed in the slides earlier. And I'll open it here. If you have the full version of Simulator with the GIC add-on, you can follow along with the same thing. If you don't have the GIC add-on, you won't be able to do the tools, or if you have the free evaluation version, it will not open this case, but you could open the 4-bus case and do something similar. But I wanted to be able to show it on a utility scale case right here. Okay, so it's the one called Texas 2000.pwb.
I had some trouble downloading that case from your link.
Oh yeah. Well, we provided, I think, 4 zip files, and within each of those, we had a maximum on our website. We have a maximum file size of, I think, 2 megabytes, which is why I broke them up into 4 different files. So here's the Texas 2000 right here, and if I go to add-ons, GIC. There was a question earlier asked about using difference flows to look at voltages. That's something that we can do in this example, and it actually is pretty interesting to see. So before we do anything more in the GIC, what I'll do is I'll solve the power flow right here, and then I'll go onto my tools ribbon, and under the difference flows, I'll tell it to set the present case as the base case. And then what we can do is we can do another power flow solution with GIC applied, and then see how the voltages change and other quantities change as well. So I'm going to switch to the single snapshot mode. This is what's in this case to begin with is actually a time series similar to the example that Tom was explaining earlier, but it's just it's got different time points and different input voltages by transmission line using the time varying series voltage inputs. In version 19 of Simulator, which is what I'm using right now because that's what's available and out there right now, there is no tab down here for telling it to create an EMP scenario. That will be in version 20. But essentially what that tool does is it generates these time points for the EMP scenario that you describe, and you describe a location, and then you describe the pattern. There's a few options based on the Oak Ridge National Lab diagrams, the different figures in the different diagrams, and you can choose which one to apply to the E3A and the E3B, and there's a few different options there. But basically, once you pick that input and you pick a location, then it'll generate a time series that looks similar to this using that tool. It's not in version 19. If I go to the single snapshot mode here, one thing I can do is choose to include the GIC in the power flow, and then I could put in a maximum field of, say, 8 volts per kilometer. I'll leave the storm orientation at 0, and I'll tell it to calculate the maximum direction value, so that what I can do is if I want to look at the worst case megavar losses in a particular area, for example, or throughout the whole system, I can find what direction that corresponds to and then study that direction and how it affects the actual voltages with the AC power flow solution. Down here is where you choose what to use for the geomagnetic latitude scaling and the Earth resistivity scaling. And for the latitude, like I mentioned, there's the equation that was shown on the slide, and then there's also a lookup table which just gives you a multiplier based on certain increments of geomagnetic latitude. And the geomagnetic latitude is not exactly the same as what you think of the geographic latitude, because of the fact that the magnetic pole is somewhere over Hudson Bay in Canada. Actually, it's skewed a little bit towards the eastern side of the U.S. So in the Pacific Northwest, you're
About 18 degrees.
yeah, it's skewed a little bit that way, and it's also actually skewed towards us. So that's kind of bad news for North America, good news for Europe and Russia and in that part of the world. But to get that, actually, and this is a file that I had forgotten to provide in the direct links, was we have a file that has the 1D Earth models in it. And if you haven't obtained it from our website yet, this is a good time to show where you can get that. If you go to PowerWorld.com, we have this online support header up here, and if you hover over that and you click on knowledge base, it opens up. We just add every time. Typically these are generated either by questions that come in that we find that we have to answer repeatedly, and we think, oh, we ought to just put a knowledge base out there about it, describe how to do things, and then maybe provide some example files and things like that. And then other things are like, in this case, we have a set of 1D Earth models that we can use, and that might change in the future. So we provide it as an auxiliary file in Simulator. It's not something that's built into Simulator. But if you go to our knowledge base, there's some filters that you can apply. For example, there's a GIC type. You could check that and then just click Go. And then it gives you things that are related to the GIC. And there's an EMP example right there that you can download. And if I scroll down, there's a Earth resistivity model for git calculations. And if you click that, it has a link to the NERC benchmark event description that was published last May. So you click that and it gives you a PDF. And then if you click this link right here, it talks about where you can download the Earth resistivity models right here. So, and then that'll give you a zip file. And if you open that, then it gives you an auxiliary file in there. So it's an Earth resistivity model. There's no power system information in it whatsoever. So it's the model. Tom showed you the slide earlier with the different regions. And again, that's open to debate as to whether or not that's good enough or if we need a better 3D model, which is much more complicated. For right now, we can put in the really, if you wanted to do your own more complex model, if you had a 3D Earth model, you could also put that information in. There's on the Substation tab right here for your case. You have a Earth resistivity scaling factor that applies to the substation, and by default, it just says use. It's kind of hard to read up there. It just says use region values. So that's for whatever corresponds to that location. But you could put in a separate value for every substation. So if you've got a pocket, like up around the graph that Tom was showing earlier that showed that little rectangle on the coast by, like, I guess it went from maybe Astoria, Oregon, up to kind of the Puget Sound area up that way. You could put in different scaling factors for substations that are within that zone. Or you could create your own. But anyway, what I'll do is I'll click Load Auxiliary here, and I'll just open this in a text file. This is just an auxiliary file. You don't have to. But it just defines, here's the beta factor right here, this 0.56, and it corresponds to the region that's defined by this boundary right here. So, and then that region is called AK-1, AP-1 is the next one. Here's the beta factor, and it's defined by this boundary. So if you had your own file that you wanted to, create your own boundaries, then you could do that too with your own factors. But anyway, what I'll do is I'll read that in, and I'll just say yes. It's asking, do you want to create these regions? And then what I can do is on my field voltage input, I can choose to use, for the alpha factor for latitude, I'll use the equation. And for the earth resistivity, I'll use the set that I just read in. And I think in order to update those values, I may have to click the calculate GIC values. And if I do that, then I can go to my substations list, and it will have an assumed magnitude right here for each substation. And Texas being at low latitude, here's the geomagnetic latitude, for example, right here. The geographic latitude for this particular substation is at 34 degrees, but its geomagnetic latitude is actually 43 because it's orientated, closer to the longitude, lines up closer to the to where the magnetic pole is. So here's a assumed electric field magnitude, and that's the 8 volts per kilometer that I put in here times the alpha and the beta factors that apply for that location. So that's what I'm seeing right here. And here's this geomagnetic latitude and ground resistivity scalar is the product of the alpha and the beta. So this times the 8 gives you this number. And there's also a field. You might have to show it because it doesn't look like it's on here by default, but if I show it, there's a geomagnetic latitude scalar and an earth resistivity region scaling, and I'll put those in there. So I can see we have different, some of these are pretty high, and some of them are pretty low. And if you have the one-line diagram that we do here, the best actually visualizing it with a contour is more effective sometimes than looking at the table. I can go to the one lines contouring right here and pick. It's actually already ready to go on this field, the substation field of the assumed E field. Just click OK on that, and it contours. So I can see there's a component, this, you can kind of tell what's going on. This all seems to be part of the same earth resistivity region, but you're seeing these different layers based on the geomagnetic latitude. And then over here, this is a different earth resistivity region, so that kind of dominates in here. But you can see that. And then if you wanted to contour just these specific alpha and beta scalars, you can do that too. So that's that. And then, of course, once I calculate the values, I could go here to the system summary and see that 89 degrees is the worst case direction. There's some slides that show 93. I think one thing that I didn't do that was described on the slides is if I come to the DC current calculation, this default here is to include everything down to 50. If you wanted to use the NERC standard at 200, I could put that in. That changes a lot of the data, but it changes the worst case orientation. Now that's 93. So I think that matches the quantity that's on the slide. I'm not going to have time to go through every slide, but that's in there. So if I wanted to, I could take a look at the system impact. If I changed the orientation to 93, I could recalculate the GIC values. Maybe that's the worst case for the whole system. And then I could look at, I could solve the power flow and then look at the bus voltages. So we could do that. We'll leave this box checked up here to include GIC in the power flow. And then I'll come out here and do a power flow solution. And if I open my message log at this point, we'll see that it has it just tells you in the log that it's including the transformer megavar losses in the power flow solution. And there's also a little notification down here. It's kind of hard to see, but it says GIC in red. That just tells you that it's including those in the solution as well. So if I wanted to contour that, I could, for example, first switch to my difference flows right here. Look at the difference case. And I could look at bus voltages, for example, graphically before I get back to the contour. I could go to my bus tables here. I'm looking at my difference case. Simulator tells me that down here. So I could sort my voltages. Again, because the latitude scalar is pretty weak, the field is only on the order of 1 or 2 volts per kilometer. There's not too much changes. We're looking at 0.01 per unit voltage change. If we wanted to look at that graphically, we could do that here as well with a contour. So we'll go into our contouring and we'll choose bus quantity, and we'll choose the field in here. If I just start typing voltage, it takes me to voltage regulation fields, and I can keep scrolling down a little bit further and choose the per unit magnitude voltage. And stored in here, there's a filter that looks just at 115 kV buses. So we'll apply that, and then there's a range assigned to the contour that's appropriate for difference flows. We're showing, in the middle, we're showing no change. Down here, we're showing a drop in voltage, and up here is a rise in voltage. And then I'll click OK on that. And then you can see how the voltages change as a result of the GIC. And other things you could do is you could stress this. So this is 8 volts per kilometer. If you wanted to, you could start to increase the field and see how that changes things. And there's other, of course, analysis that you could do. I could, we'll just go from 8 to say 15 volts per kilometer, resolve the power flow, and then update the contour. So see that the voltages drop even more and it becomes more widespread. And you could keep pushing that out until you get to voltage collapse. See where those thresholds are, things like that.
But you don't have to change the direction at all, right? That 90 degrees.
You can if you want, but I didn't. Yeah, right there. Yeah. So anyway, that's the example. And then there's a few other things. Let me go through a few of the slides right here. And then we'll talk also about, there's some sensitivity analysis tools that you can look at to see, for example, for a particular transformer, where are the transmission lines that contribute GIC to that transformer. But just come down here through the slides, there's the benchmark event right there, voltage contours. So again, this is on our knowledge base. You can download stuff like this. Like I said, we do have the time series that you can download, and that comes in the form of an auxiliary file. We also have a spreadsheet that you can input. You run the time series from the auxiliary file here, and then you put in a transformer. You can create a transformer filter and then run the auxiliary file, and it will dump out a CSV file that has the effective GIC time series for transformers that meet the filter, and then you could run those through a thermal response calculator. We have a spreadsheet that you can download that uses a first order model, and within the spreadsheet you can change parameters, things like that. So sensitivity analysis, there's a, let's go to that right now. I'm going to change this back to 8 volts per kilometer again and recalculate the GIC values. Down here on sensitivity analysis, you can, let me switch back also to, I'm in my difference case right now. I want to switch back to my present case. So I'll go to Tools, difference flows. Switch back to the present case, and then make sure I click calculate gig values to make sure I've got the right ones. So here, there's a couple different sensitivities that you can look at. The transformer I effective sensitivity. And one of the things that you could do with this is you could sort your transformers by per phase effective GIC, either in per unit or in amps. You're going to get the same sort order. The one that's first on the list is kind of uninteresting because it only has one 345 kV line coming into that bus. It looks, I'll show you the bus view one line here. So yeah, here's the actually it's two lines, but they're in parallel from the same other substation. So the sensitivity analysis results that we get from this are actually pretty uninteresting because it just tells you that the GIC comes mostly from these transmission lines, which makes sense because it's right in series with that transformer. The second one on the list is a little bit more interesting, although the results are mainly the lines that come into it. But here's the transformer, and then on the 345 kV side, we have several different transmission lines coming in from different substations. And if I wanted to see, well, which one of those are contributing to the GIC, I could include that transformer in the sensitivity. You can put as many transformers as you want to. It'll just, because these are linear factors, it just can superimpose the results. And then you can choose, if it's a transformer sensitivity, you can choose that the assumed field direction is either parallel to the line or in a certain direction. Parallel to the line would be the worst case for that transmission line. And then when I click recalculate sensitivities, I could look at, for example, the change in effective current per E field and sort that in descending order. So it tells me which transmission lines have the biggest impact on the effective current in the transformers that you select up here. So you could use that information to say maybe a remedial action might be to open some of these transmission lines, or maybe maybe if it's practical to install series compensation on one or more of those lines, we could do that. You can make that change in the case and then resimulate it and see what's the impact. There's another calculation called, let's see if we look at, you can look at line amp input sensitivity, which is kind of the inverse of this calculation, where you're specifying a transmission line and you say if you have, for example, one more amp of GIC flowing down that line, which transformers are impacted by that. So that's the sensitivity here, and see an example. We pick one of the lines in the example that goes in to there. So let's see, from bus 1842 to 1842 to 1802. That's one of the lines that's incident to this. It's this transmission line right here. That comes in. So we could say, for example, if we have one more amp of GIC being put on this line, which transformers does it go to? So for that, you would put an assumed injection of amps. And it's all linear, so if I put in 1 amp, I'll get some values. If I put in 2 amps, I'll get twice the value. But then I can click recalculate sensitivities there, and then you can sort here, and you get a list of transformers down here, so you see which transformers that GIC goes to. So one thing about this sensitivity, if you want to get back to just the GIC, it uses the whole GIC calculation in the G matrix to push those out. So if I want to get back just to the base GIC values, I have to click calculate GIC values. And then finally on these options here, you can click choose substation driving point values. If you do that, it gives you a Thevenin ratio, which is described on a slide, which can tell you, you can sort on high, like high voltage substations, And see, the ones that have the higher driving point resistance are the ones that have where the resistance that's assumed for the grounding of that substation, the ratio of that substation's grounding resistance to the grounding resistance plus the Thevenin equivalent of the whole rest of the network. So you can see, this can be a screening tool to see which substations maybe you need to go out and get good grounding resistance data for. You can look at, you do a first cut where you don't know the grounding resistance and say, based on the whole network and the transmission lines and looking out from each substation to the rest of the network, which substations have high Thevenin ratios here. So, and then you can sort that, or you can sort, based on the calculated amps to neutral and see which ones of those have high, right here actually, high Thevenin ratios right here. So if you look at, amps to neutral, you can see which ones of those have the highest Thevenin ratios. And maybe, this one right here might be one where we want to make sure we have the ratio is 0.7. We want to make sure that we have a good grounding resistance put in for that one. So, yeah, and then other things you can do too. I'm not going to go through this in detail in the interest of time, but I can stay a little bit afterwards if people have questions. On the transformer records, you can choose to add neutral blocking. It's going to be like a very high resistance or a capacitive neutral blocking. It'll block the GIC from going down into the neutral of that transformer. If you set that to yes, and then you can recalculate, resimulate your GICs and see how that changes things.
Is that in the options or?
Yes, it's on the transformer records. Again, right here.
Is that some kind of a solid state device?
It's whatever device you can obtain, I guess. There's a company called Imprimis that's out peddling these things, and probably a few others.
On the distribution side?
What's that?
On the distribution side transformers, or even on
I think the way they would do it is it would be in series with the neutrals.
device?
Right. So you could put it. I mean, I think ideally what they would want to do is you go into one substation and block all the transformers in the same substation, through the neutral. But yeah, it's a transformer field in here. Where is it? Get blocked for transformer neutral. So you could toggle that to yes for one or more transformers, and so on. So there's our quick power flow list has some GIC information in it. That's what that says. You can also download from our website, and I'll just open it in Simulator right here real quick. In the NERC application guide, Appendix 2, there is a sample 6-bus system, which is actually very similar to the 4-bus one that we initially worked with, except for they plop another substation with an autotransformer in the middle, so you get a little bit different topology there. And then these 3 substations have locations. All these input parameters match what's in that example. So you can, just to see how the calculations work, you can compare the results that you get from the application guide and see that they're the same. But you can download this example from our knowledge base here. I think, where is it? Right here. So NERC, it has a link to the NERC application guide, and then you can download the 6-bus case here, or from the files that we had sent out prior to this meeting. So this is just what the case looks like, and again, there's a grounded Y delta GSU at either end, and then an autotransformer in the middle. Okay, and then the example Tom went through earlier, he was looking at transient stability. So certainly for the high altitude EMPs, it kind of makes sense. And if you want to generate a time series for transformers, you might use the transient stability tool and just calculate the GICs for that. So just an example that we could use here. And is anybody else needing to leave, or do you want me to run through this example? I can do that. It probably takes 10 or 15 minutes. Okay, we'll just carry on. We'll get through this example and then wrap up there. So yeah, from the 6-bus case, we can go to our GIC input right here. And then instead of single snapshot, we can choose the time varying. And again, these can be EMP inputs. They can be really just any time varying inputs. You can create them based on assumed field parameters at a certain time and build them up here. What's in this case to begin with, I think we have 6 different time points that actually correspond to different field orientations. But I'm going to delete those first. So just on this time varying series inputs, I'll choose to delete all of them. That'll clear that out. And then if you wanted to create your own, the way you would do it is you would say at a given time, we'll put in a field of, let's say at time 0, let's make the field 0. So that it'll ramp up to a certain value and then come back down. We'll just add a 0 at time 0, and I think we'll add a 0 also at 10 seconds. So we'll put a time of 10 seconds and add another 0, and then at time 5 seconds we'll put in 15 volts per kilometer. So that's down here, the maximum field and the direction. And at 90 degrees, which is what's already in the case. So if we add that. So you have the time points right here, and then for each transmission line, you have the DC input voltage that's shown in here. It's not really that user-friendly for describing the transmission lines. It's just each transmission line is described from its from bus to bus. So, but normally you don't have to interact directly with each one. If you wanted to change that value for a certain transmission line, you could. But normally you're going to use a starting point as the field that you described here, or you might use an EMP event as being the starting point. So you don't really have to interact with this diagram other than to verify that you have some time points added. And then what you can do up here is you can change the time in the power flow, for example, to any arbitrary time in this is seconds, and then click calculate GIC values, and between time points where there is input data, it'll just linearly interpolate from between the time points. So I can put in 3 seconds and say calculate GIC values. I can go out to the transformers, for example, and look at the GICs for the transformers. I have some quantities on my one-line diagram as well that reflect what's happening at that time. So, and then if I wanted to run this through transient stability, what I would do is I would go to my transient stability dialog on the add-ons here, open transient stability. And as Tom mentioned earlier, we have a couple options on transient stability. On the power system model right here, the first one is to include the GIC effects. The other option that Tom mentioned is only available in Simulator 20, which I don't have here, but the other one is to just run the GICs without doing the dynamic simulation. So the advantage of that is it's much faster, and if you just want to generate a transformer time series, you could use that option to run through very quickly. This is a small case, so we can actually do a transient stability simulation fairly quickly. So yeah, you just need to make sure that you include the GIC effects. And then typically, if you're analyzing a GIC, you wouldn't have any fault events that you would also throw in on top of it. But if you did want to say, for example, that something else would happen during that GIC event, you could put those in as events in transient stability. I'm not going to go through all the details of using our transient stability tool here because that's another potentially days worth of material or more on that. So suffice to say, you can come in here and just choose to include the GIC effects. On our simulation parameters, I'll leave these the way they're described here. We're going to start at time 0, end at 15 seconds, and we're going to use a time step of 0.25. And if we want to look at, there's some basic models that are included in here. I think there's a generator machine model and an exciter model for the two generators. If I go into my model explorer here, I can see, yeah, I've got some IEEE T1 exciters that are the active ones for the two generators, and then there's some other exciters that we added in here, but they're not active, and you can see how those different exciter models with different parameters impact things. I'm not going to go into too much of the detail on that, but you can also see they have the Gen Rao machine model. So that's what's being applied. And then in my transient stability analysis, I'll just click Run Transient Stability, and it's marching through right here. And I think there's some plots that it'll generate when it's done. Yeah, there's a few plots. So we'll see those when it finishes the 15-second simulation. So just while we're waiting for that, just come back to the slides here and see that, yeah, there's that option that you can choose. And the plots are going to come out, and that's what we'll see. So yeah, one of the questions I mentioned earlier is that, or one of the things that's kind of being discussed as far as longer duration events are concerned, this is just a 10-second event that we kind of made up, but you could plot out the bus voltages and the generator megavar outputs, and we can see that this generator exceeded the power flow limit of 50 megavars for several seconds. Maybe that's okay, that maybe the overexcitation limiter wouldn't kick in until several more seconds. But if you have a longer event, then maybe that's something that you want to model in the transient stability too. So yeah, here's the output plots right here. That's a rotor angle right there, bus frequency. So you can kind of see how that varies. So yeah, we have the tools obviously to be able to input these GIC effects into transient stability. Here's the transformer. This is nice and linear, of course, because this is the I effective, and we could use this as a starting point to plug this into a thermal model to see if these transformers would heat up too much. But that's how much GIC is flowing through each of the three. Megavar losses. Generator megavars. These are not linear because the megavar losses look like a constant current load because they're proportional to the voltage. So as the bus per unit voltage is varying, according to this right here, as the GICs ramp up and the voltages drop, then you actually get less megavar loss because it's a constant current megavar load. So we can look at field. This is the field current inside one of the generators. So again, all the transient stability tools that are available in simulator you can use for the GIC or EMP events. And we can see on this, if we change the parameters, I think to at least, what does it say there, 20 volts per kilometer, then we would see collapse in the transient stability simulation. I think the power flow will actually collapse at less than that. So if we went over to, but that's because you're getting more VARs out of the generator in the transient stability simulation. If I come over to the power flow side here and choose single snapshot mode, I got to get out of. So when you're running transient stability, it'll leave you in that mode until you tell it to restore the reference. So if you wanted to bounce back to the power flow, you would want to come back into transient stability and say restore reference. So I can do that. Then I can come back over to the GIC, and if I put a current field, let's see if 15 volts per kilometer, and say calculate the GIC values and include it in the power flow solution, I actually get a collapse. I think right around 12 volts is kind of where that happens. But let's see if I change it to 10. Change it to 10 volts per kilometer. We can get a solution, but we've got some pretty... Does this show the AC? No, this doesn't show the AC voltages on the one-line diagram. I'll go back to my form here. I can see my bus voltages are getting kind of low, just at 10 volts per kilometer. If I get to 12 or 15, it's going to collapse here. Transient stability will ride through at 15. I could get a starting power flow solution back here. I could go back to my transient stability and play with that as well. Actually, but to do that, I have to change the time series input. At time 5, let's ramp up the maximum field to 20 volts per kilometer. Change that. So now all these input voltages change accordingly. And I could come back to my transient stability, rerun that, and I think this will diverge before we get to the 5-second peak. So. Oh, actually it did right through that. Might be with a different exciter model that it collapses, but anyway. Just in summary, there's a lot to study. Certainly a large GMD event or a large EMP event could affect a lot of different things, a lot of different assumptions that go into it, and our knowledge and our ability to model things is still developing, still evolving. Our goal is just to, as Tom mentioned, to be able to put the tools out there, and as the industry continues to move forward, continue to evolve the tool to keep up with that. So, yeah, actually, no, this didn't collapse. I think it's with one of the different exciter models anyway. It collapses, but because we have the IEEE T1 exciter models in here right now. If you activated one of those others, like the AC7 or the AC8, I think that is a little bit less stable in terms of providing the VAR support.